countries of broadcasting, and we still don't know how to go live. Oh, we're live.
It's yellow.
3, 2, 1. Hello, dearies. Welcome to Undersampled Radio, episode 86. We're broadcasting today from two places in Austin because we couldn't get our act together. As you may know, it is South by Southwest this week. You may not know that, actually, because it's probably taking our editor 6 weeks to publish this episode. But we are live and direct from Austin,
South by Southwest 2019. Just in case it takes a really long time.
Thank you. I don't really know what South by Southwest. Let's kick this episode off with a informative segment we call Teach Graham what South by Southwest is. So to do this, we are going to introduce a much more familiar Austinite than myself, and then we'll go into news. Shocking, I know. We're changing our show format. It's never happened before. We have with us today Matt Jaffee. Hey, Matt.
Hey, how's it going?
What is happening over there? Are you in downtown Austin or where?
I am in the southernmost part of Austin, down in Circle C Ranch in my home. So I've managed to avoid South by Southwest for most of the week.
Yeah.
I did get caught on a $30 parking charge once, but otherwise I've been pretty lucky.
Okay, so maybe you can tell me. So as some of our listeners know, I haven't even lived in Austin for 2 years, and I don't really still understand what the deal is with South by Southwest. So there's like a tech conference and music stuff. What is the layout?
Yeah, unfortunately, I've only been here a little bit longer than you have. I did kind of attend it my first year here, and it's like a sprawling conference / party / vendor showcase, and it's got tech and music and all kinds of stuff. And it really kind of takes up the whole city while it's going on. It's just general insanity. And I think it's grown a lot in the past few years, and it's becoming kind of corporate and crazy. But yeah, it's definitely an interesting time to be in Austin. But I think a lot of the locals aren't huge fans of it.
Okay, so it's 1 week.
I think it's over a few weeks, actually.
Oh,
yeah.
The different portions, because there's like the tech portion, and then there's, I think, a music portion, and there might be like a film portion.
Okay. So I have some friends coming to town this weekend. Should be here in 2 hours, and I want to go do something. I figure it's South by Southwest and they'll be here, so let's try to do something. I guess, tell me if this is a bad idea. My plan is tomorrow we're just gonna go walk around downtown and see what's going on. Maybe stop in here and there.
Yeah, there should be plenty of wacky things to just pop into. I heard there was like some kind of robot display on Cesar Chavez that Sony was doing, where they've got I don't know, some kind of like AI type thing where these robots are like trying to learn behaviors from the crowds as they go by or something like that. So, there should be all kinds of wacky stuff like that all over downtown.
Awesome.
It sounds like sort of CES meets Burning Man meets Google Next or something.
That's a pretty good description, I'd say.
Yeah, it sounds crazy. I sort of haven't been, but I came across it. The phenomenon, it seemed like it was really connected with the start of blogging and kind of, I don't know I suppose that's social media stuff. But I've been feeling like blogging's really changed over the last few years. Like there's a different feel, so I can see how South by Southwest must have evolved or devolved or something to
side-volved.
Yeah, like pivoted, I guess. Because that whole landscape is just so different now from what it was kind of 10 years ago. But yeah, sounds pretty cool. We don't really have a lot of stuff like that happening in Nova Scotia, where I live.
No, by the way, that's in Nova Scotia.
There's a couple of little conferences around web tech and stuff like that. But those I'm an hour away from the city, so we did just start a meetup, a computer sort of machine learning slash.
How many people go?
Don't make fun of me. I don't know. Maybe there were like 9 of us at the last one.
Wow, that's actually
double digits.
Yeah.
Well, I think we could hit double digits at some point. No, it's
kind of nice to keep it that small. You can have like homework assignments and things.
That's right. Yeah, we'll see where it goes. But I'm really hoping to. Someone was threatening to do like a show and tell, hands-on with Unity last time, so that would be fun. I'd like that.
Yeah.
So I hope there's more of that.
So I heard that Pick This is resurrected from the dead.
Yeah, seems like it for now. Seems to be making a bit of a comeback. We built this thing, Matt, that's I've sort of described it as like Stack Overflow for images, which obviously makes it sound much more important than it actually is. But basically, it's a way to ask questions about images, or rather questions that require a sort of graphical drawing for an answer. So we can kind of crowdsource answers to these kind of spatial questions. So it's aimed at people who interpret images for a living, like geophysicists, radiologists,
interesting.
That kind of thing.
That's pretty cool, actually. That kind of reminds me, when I was in grad school, I did a sort of summer project where I was looking for pulsars in all this radio telescope data. And a lot of that was just like getting really good at recognizing patterns in these graphs, graphs basically that are just kind of bitmap images. And so after a while, you could be like, oh no, that's definitely fake. That's definitely fake. There's nothing there. Definitely fake. Because when you're looking for, when you've got like a ridiculously powerful radio telescope and you're looking for signals from pulsars that are 100 million light years away or whatever, it turns out there's a lot of interference that can make fake signals. Like microwaves and cars and just anything that produces radio waves.
Oh, when you say microwaves, you're talking about actual.
Yes.
Microwaves in the kitchen.
Well, and the microwaves that they emit. Yeah.
What's the sample rate of the data?
I do not remember. I think I said grad school, but I actually meant college. This was a while ago.
Yeah. So you're not an astronomer / astrophysics.
No, my bachelor's degree was in astrophysics, and then I pretty quickly migrated to computer science for master's and all my career.
Jaffee works at a company called Pelosa, which is building a distributed bitmap index, which we'll talk about momentarily. But since we're on it, what happened after college and grad school? How did you kind of like get into the computer science world?
So in college, I guess, I'd been interested in programming and computers in high school. And I kind of went the physics route in college, but I was still taking comp sci classes. And I minored in computer science. And then I ended up getting into a graduate program in computer science. And I was like, you know what? I think I'm going to do this. And so then I did that. I met some really smart people, worked with some really smart people. And after I got my master's, I was like, I want to like build software. I want to like, write real programs, not just kind of fiddle around in academia. And so I was like, I'm going to go get a job. And I got a job for a government contractor in the DC area. And that kind of had some ups and downs. I did a very wide variety of things there. I did like web development. I did some Java and some Clojure, doing like data pipelines and ETL stuff. I did a desktop GUI app in Python. I did sort of like an internal skunks work type project doing using GPUs to look at network traffic and scan for patterns in network traffic.
Cool.
So like a really interesting kind of wide breadth of stuff. It was the kind of place where they were like, oh, you think you can do Python? All right, we'll put you on this project. Oh, a little Java? We'll put you on this project.
Yeah. That's a great way to start your career, right?
It was, to be honest. We eventually kind of got tired of the DC area and wanted to move someplace warmer. And so that's how I ended up coming to Austin and started working for this company called Humble, where Pelosa was actually built. And then a couple years after that, we spun Pelosa out.
You did what? You spun Pelosa. Oh, it started off as a sort of one project inside another company.
Yeah.
And then it kind of took on a life of its own, right?
Yes. It was pretty interesting. And I wasn't involved in the details of the spin out, but my understanding is that it was quite difficult to perform that maneuver, sort of just like getting all the tax implications right, and you know, getting all the investors on board, and just kind of making that happen is not an easy thing. But the management team did it, and now we're a totally independent company, which is pretty cool.
Yeah. So give us, what is it? What is Pelosa?
So kind of depends who you ask. You know, if you ask our CEO, he'll give you like this like super vision heavy answer of, you know, like far future, like, you know, we want to be the integration platform for every algorithm, and, you know, or something like that. But I mean, at its core, it's just it's an index, and so, you know, databases have indexes inside them, and Pelosa is really just the index part. And so there aren't too many things like that. Even things that call themselves indexes, like Elasticsearch, they really start by kind of storing your data in the normal database type way, and then they build indexes on top of it. And Pelosa just starts with your data indexed, and it turns out that has some nice properties for sort of scalability and query performance. And so, I mean, the main reason that Pelosa exists is for performance, because, you know, we were at Humble, we were trying to build this crazy UI for marketers that let them slice and dice over all their customer data, and you know, each page was making like tens or hundreds of queries, and so we needed each query to return in, you know, just a few milliseconds.
What is Humble? It's a customer 360 app or something.
Yeah, it's like a customer data platform focused on like the sports and entertainment market. Yeah, basically it was like a web tool for marketers to get a broad view of all their data and then drill down into different segments and figure out, you know, who they wanted to like send a certain email to, or, you know, or just learn about their user base.
Gotcha. Okay. So when you spun this thing out, how did you, I mean, what pieces of the tech did you take? Was it just all ideas? I mean, were you guys able to retain any actual building blocks?
Oh yeah. I mean, so Pelosa was built at Humble, but it was like a totally separate thing. And so most of Humble was like this big kind of like Django Python app. And we built Pelosa as basically a supplemental backend sort of data store to answer some of these really hard queries that were, you know, making Elasticsearch fall over or whatever. And so when we spun out, I mean, it was pretty clear, like, oh, like, this is Pelosa, it's in this repository, right? And then we ended up open sourcing it shortly thereafter, which I'm a huge fan of. And yeah, I mean, it was pretty clear kind of where the IP was demarcated.
Yeah, that's really cool. So was that a deliberate move right at the beginning to be quite kind of modular? I mean, I guess an indexing sort of service is always going to be pretty standalone, right? I mean, you know, but was there a thought that it might be a thing on its own? I'm guessing there wasn't. Seems like.
I think once it was built and the first queries started hitting it, I wasn't there at that time. I joined shortly thereafter. But I think around that time, they started to think like, you know, this is probably bigger than what Humble's going to use it for, because it was just so much more performant, you know, for the types of queries they were trying to do than anything else they'd tried. And they'd been through a lot of different open source, you know, data solutions at that point, like Rethink and is it Rethink, or I don't know. I mean, everything that was available at the time.
So Humble became the first customer, basically,
yeah,
for this new thing, and then like the core technology was open sourced, was it?
Yeah, we open sourced the whole thing shortly after we spun out. Basically, I was like, nobody's going to take like a database seriously in 2017 or whatever it was, unless it's open source, was kind of my feeling. I mean, I definitely wouldn't as a developer. I'm not like looking at proprietary solutions like, oh yeah, I want to use that. I mean, some people still do. It's not, it's not like it's impossible, but you know, it just doesn't seem very exciting. And I think it was the right choice. I mean, we've had a lot of good interest come from the community, and then you know, start down the path towards converting to, you know, like an actual customer that's paying us for support or enterprise license or whatever it is.
Yeah. Seems like very much a sorry, Grant, but like very much a developer's tool, right? I think when you're the open source story is a relatively, it's an easier sell when it's other devs that you're talking to, because they get it. Because like you, they don't want closed source stuff. But that's really cool. And so what I'm going to ask about later after Graham's question is like what the business model sort of consists of, because I'm really interested in how you make money basically with open source at the core of your business. But
yeah, me too.
Graham, you were
no. Go on, please.
sorry. So yeah, so I mean, you know, like is it you know, the model that sort of first comes to mind for a lot of computery people is kind of Red Hat, right, where you've got like fundamentally open source piece at the middle, and then you sell support, maintenance, software. I get other software, services, training around that central piece. Like, what's your guys' thing?
Yeah, so there are a lot of models, and I think it's pretty widely believed that the Red Hat model like won't work again, right? And whether that's true or not doesn't really matter, because no one's going to invest in it. So,
right.
And so what we're doing right now is kind of a hybrid where, you know, we've had enough interest in like basically like support and like feature prioritization and that kind of thing that we're getting some contracts around that. But what we really want to do is wrap a managed service around Pelosa that you know, we can sell as like a cloud service basically. And so I think people are a lot more willing to just basically pay for that ease of use and like not having the operational overhead. But Pelosa is still in a place where it's a low enough level tool that most organizations need some help getting going. And so I think we're kind of using that to bootstrap our way into a fully managed service kind of thing.
Right. Very cool. And it's going well. Like the things look rosy.
Yeah. I mean, we've got a few customers and potential customers who are pushing various parts of Pelosa kind of to the edge, and us being like, oh, well, yeah, it does use a lot of memory in that situation. And, or like, oh, like, yeah, the scaling doesn't work in that direction. We'll have to do something about that. And so we've had a lot of really good feedback from some really big users. And, you know, and it's nothing that's like, oh, it's totally broken, like we have to shut down. But it's all stuff that, you know, we can address, and it's fun engineering problems. So yeah, it's going quite well, and I'm consistently excited to come to work and try to figure these things out.
Yeah, right.
How does it work? Wait, first of all, what is a bitmap index?
All right. So let's see. Let's take a database table that is it's the people table. So each record is a person, and one of the columns is shirt color, right? And so it has different values like red, green, blue, orange, yellow, etc. And so normally how you would store that is, you know, like record 1, red, and, you know, record 2, green, record 3, blue, and all the other columns, right, on each one. And what a bitmap index does is it says, here's my record. Is the shirt red? Is the shirt green? Is the shirt blue? Is the shirt orange? Is the shirt yellow? So it basically has, instead of that one column, it has n columns, one for each color, and each column is a single bit. And so whether that bit is set or not represents whether the person's shirt is that color. And so if you want to say, find all the people who have red shirts or blue shirts, but not green shirts, then you take the red shirt bitmap and the blue shirt bitmap and you union them together, and then you subtract out the green shirt bitmap. And so, I mean, you could imagine someone has shirts with several colors on them, so they might have multiple bits set. And basically what that allows you to do is really, really fast types of, like those types of segmentation queries. And it's not immediately obvious, but it also allows you to do pretty fast like aggregations, like group bys and filtered group bys. And there's also a pretty clever way to store like integer values without sort of exploding your space requirements. And so you can do range queries across integers, which sort of opens up the ability to do time and a lot of other things.
I was wondering about that.
Yeah, so we have this one core data structure, and we have a super, super optimized implementation of it at the lowest level, and we use it for everything. And it's so much nicer than having like multiple different indexing solutions and then having to try to interoperate them. Because every operation, you get a bitmap out, and it's distributed across a cluster, and it's all sharded out. But each operation gives you a bitmap, and each operation takes in a bitmap or several bitmaps. And so you can sort of infinitely nest queries and you know, do whatever you need to do. And at the core, it's all using a pretty small piece of code, you know, that's running all this stuff. And so it's pretty easy to manage, even as, you know, just a small group of developers.
So like when I hear the word bitmap, I think of images, but it sounds like this is more like bits, as in binary, like on and off.
Yes, it's actually a bit set. So it's a way to represent a set of integers by whether or not a bit is set in a certain position in just one long chain of bits.
Right. So what you described earlier sounds like one hot encoding, right? That sounds like it's related.
Yeah, I think so.
Where instead of storing a label, you store whether something has a label or not.
Yeah,
like of classes. So I mean, but your shirt color example was spot on, right, Graham?
Right. How do you store floats?
So we don't right now.
Oh.
We have done some research into it. It looks pretty feasible. There's not a lot of demand for it for us that we've seen. So we kind of put it on the back burner. You know, obviously, if you don't need like, you know, to whatever your precision you need, you know, you can multiply or divide your number, turn it into an integer, and store it as an integer. But that obviously doesn't work for applications that need to go like super small and large, or, you know, whatever.
I mean, that's kind of how floats work anyway, isn't it? I mean, that's how they're implemented, essentially. This is a bunch of integers.
IEEE, yeah.
Yeah. And so that's effectively like what we would do. We would have like the significand and the exponent and the sign bit and do some internal stuff to sort of figure it out when you put in a range query or whatever. But it's just not number one on our priority list, and we've got somewhere less than 10 developers, so we have to kind of pick and choose what we're working on.
Okay, so how do you store ints then without? I mean, it seems like you have to limit the dynamic range.
Right. So the naive way would just be to have a bitmap for every value, and so you know, we use a compression format for bitmaps. It's very nice and very good, but having, you know, 4 billion bitmaps would still be a little bit rough. And so what we do is we actually store the binary representation of the integer in however many bitmaps we need to store the range of integers that you want to store. So if you have integers that go from 0 to 1,000, then we only need 10 bitmaps. So because it's 2 to the 10. And if you have integers that go from 0 to 4 billion, then we need 32 bitmaps. And I won't necessarily dive into it, but it turns out that you can construct queries over arbitrary ranges by intersecting and unioning and differencing those bitmaps to get out a bit set that represents all the records that fall within that range and none of the records that don't.
Huh.
That's really cool.
It's called bit sliced indexing, and we have a pretty detailed blog post if you do want to know more about that. The interesting thing about that is that I'm not sure that any other system uses that. I mean, lots of systems use bitmap indexes, but I don't know of any that use bit sliced indexing.
And can you, compressing these bit set things, that would be run length encoding, or can you do better than that?
Yes. So we use a format called roaring, developed by a guy named Daniel Lemire, who is actually in Montreal, I believe.
Yeah, I read his blog.
Yeah, his blog's awesome. And so what roaring does is it's so simple, but it's so incredibly effective. It has 3 different encoding types. One is just a bitmap, like you just store the bits. And so that's good for sort of high entropy, high information density type data.
Okay.
And then another is an array. You just store an array of integers that represent your bit set. And so that's good for really, really sparse data. And the other is, you guessed it, run length encoding, which is good for super, super dense bitmaps, where, and it turns out there's a lot of times where you have every bit set for a long run. And so using run length encoding makes that trivial to compute on. But the really interesting thing about roaring is every operation, whether it's in a logical and, a logical or, a not, whatever it is defined on every pair of possible encodings. So you never have to like encode or decode or like convert representations. Yeah, you just do your operation. So we have like a union array bitmap, union array run. So the implementation's a little bit more complex, but it's just ridiculously fast.
Yeah, that's really interesting. I've been playing around recently with, I don't even know what, I'm not a computer scientist or really a scientist, or a mathematician or anything, but
he's all of those things.
It's, well, yeah.
Yeah, I could sense the false modesty just radiating.
But
or maybe it was real modesty, but it's misplaced.
So anyway, so I don't know what to call this, but the thing that I'm doing seems like spatial indexing. So like what a GIS does, but it's one-dimensional, which seems like it should be easier, and it probably is easier. But when you're writing the code, it's sort of still a bit of a mind bender sometimes, right? But what I love is how there is this sort of fundamental set of operations, like, sort of unions and differences and so on, that once you've got them, you can do almost anything. It's kind of magical. It's like, I don't know what you'd call them. They're almost like axiomatic.
You would call that
operators.
You would call that a ring, right?
A ring.
Where's my mathematician? Yeah.
What is this? This is like
set theory.
What? It's set theory?
Yeah.
Okay.
So yeah. So one operation defines an algebra. Oh wait. Fuck, I can't remember. It's, what is it? 2 operations over a group define an algebra, and a complete set of operations defines a ring. I can't remember, but it seems like that's what you're defining here.
I don't know what you're talking about, but it's giving me goosebumps.
All I know is that you don't need much more than not and to be Turing complete.
Right. Right. Yeah, it's pretty interesting.
Okay, wait. I have another question. We covered bitmap index now, but we didn't cover distributed. What does that mean?
Oh, yeah.
It just means you can put it on a bunch of computers at the same time.
How do you do that? It seems like one bitmap. So, okay, so you break a bitmap into multiple pieces and store them on multiple computers?
Right, so we shard it. And so basically you would take, our default is 2 to the 20 records, which is about 1 million records. And we actually,
Wait, what do you mean? Say that again. Your default.
our default shard width is 2 to the 20. So that means you have a bit. Say you have in our previous example, you have 1 billion people in your data store, and so you have 1 billion records, and we would break that up into about 1,000 pieces because there's 1 million people in each shard, and those get distributed across the cluster. And so that might mean that they're just on one really big node that has 96 processors or whatever, or it might mean that they're on a cluster of 20 nodes, that each have 8 cores or whatever. And that sort of unit of sharding is not just for distributing across nodes, it's actually sort of the unit of concurrency within Pelosa too. Now, I know you folks use Python, so this might be a little unfamiliar, but you can actually use all the cores in one machine at the same time. I'm just messing.
Nonsense.
Wait. So you must have an index. Do you guys write your own index to do that sharding? Do you have like a bitmap that is the index to where the pieces are sitting?
Kind of. Actually, to figure out where each piece is, we use a hash, a consistent hash. And so you take the index name and the shard number and you hash that, and it goes to a point on a ring, and then you sort of map the nodes that you have onto that ring in such a way that if you add a node, you have to kind of do the minimum amount of shuffling to get all the shards where they need to be. And that's a pretty typical strategy that most like distributed storage things use. But what was I going to say? Oh, right. We actually do use a bitmap to show which shards have data. So internally, when we're talking about like which shards have data, versus which don't, because sometimes there's gaps.
That way you don't have to map across all of them when you're doing analysis.
Right, exactly. And so we were like, okay, so like we're going to keep track of which shards have data, but you might have like thousands and thousands of shards. That's kind of like annoying to pass around. Oh, well, we can just represent that as a bitmap. We already have this nice library here.
That's awesome. That's awesome. Okay, so going one level more abstracted, how do you actually interface with this system to perform analytics? So I can sort of conceptually see how you do a filter, but from there, how do you interact with the data?
Right. So that's a fantastic question, and it's one that we're really trying to figure out the right answer to. I mean, we have a query language that's really simple that we developed that lets you do counts and intersections and unions and differences and XORs. And I don't really know what XOR is good for, but we've got it. And it'll probably be good for something. And then we've also added on top of that like group bys and top ends, where you can say like, give me the top colors. I want the top colors by how many people are wearing a shirt of that color. And what's really cool about that is you can also filter it. And so maybe you would say, I want the top colors, but just for females from Connecticut, right, or something like that. And you can get that list of top colors. And then when we added group by, you can actually do that over multiple fields at a time. So it's like, I don't know, if we had shirt color, well, yeah, you could do every shirt color gender combination and the count of people who had that. And you could do that for some arbitrary filter as well. So it's getting to a point where we can start to see, we have visibility into like just trying to support something like SQL. Because we've got select, count, group by, where. It's pretty easy to see how we can do halving. And in some cases, joins are actually trivial. In some cases, they're not. But so, for example, in the shirt color example, you would in a SQL database, you either have a column that's color and it's a string, Or if people can have shirts of multiple different colors, then you have to have some kind of like many to many with like, you know, like another table in the middle, and it gets a little bit messy, right? Whereas in Pelosa, it just sort of naturally supports that. You just set another bit, and then that person now, you know, has both colors of shirt on. And so in that case where you would normally have to do some kind of join thing, it's just already there. It's actually harder for Pelosa to do the mutually exclusive case where every person only has one shirt color.
Yeah. Yeah. Okay. So when you're, okay. Yeah. So we're interacting with the data that way. And then there must be some sort of, you need a translator or something to, like in the case of categorical data, to map from bits to back to data to do whatever, like mathematics on the data.
Yeah. And so there's a couple options for that. Pelosa has an internal one, or you can sort of map your data ahead of time and have something external that's storing like what the numbers represent. And there's pros and cons to each. So really, because when you do a query in Pelosa, you're either getting back like a count, or you're getting back just a bunch of IDs that are indexes into, you know, into the bitmap, whether it's row indexes, or sorry, our terminology is like backwards. So, but whether it's column indexes, which would give you actual values, so like the color red or the color blue, or it's row indexes, and I'm actually inverting our terminology so that it makes a little more sense, or it's row indexes, which would give you like, this is the identifier for a person. And so you wouldn't store like an email address in Pelosa, because pretty much every person has one email address, right? And there'd be no point in having that indexed. And so you get that ID back or whatever, and then you can go look up in like a really fast key value store or something, you know, that single ID or that small set of IDs, and get the non-indexed data like email addresses or whatever.
Have you guys done math on the bits? Seems like, I mean, you could definitely build, I do a lot of deep learning work. So, I mean, you could definitely build a neural network, which would take data in bit form and process it. Have you done any of this?
Yeah, so actually right before we spun out of Humble, we did a project where we implemented a by-click enumeration, a maximal by-click enumeration algorithm. And so basically that's, you can think of Pelosa as a representation of a graph where, so it's, we've got a bunch of bitmaps, right? And so that's basically a bit matrix. And so a bit matrix you could think of as an adjacency matrix, which could be a graph representation where each row, if a row has an edge, or sorry, if a row, if there's an edge between two nodes, then there's a set bit at a particular position that says like row 37 is a node, and column 22 is a node, and a set bit means that there's an edge between them. And so at Humble we had like people and just for example, Facebook pages that people like, and there's like 50 million Facebook pages, and we've got like 300 million people or whatever. And we wanted to find clicks. We wanted to find highly connected groups where a whole bunch of people liked some subset of Facebook pages. Because that's really interesting to marketers, right? Like, oh, there's this like interesting subculture of people that we can market to in a specific way or something. And it turns out that enumerating these clicks and finding maximal clicks is fairly computationally expensive, but we implemented a way to do that in Pelosa that was, you know, faster. And it's still an expensive thing to do, but when you're doing it on raw bits and you can sort of, you have a lot of concurrency at your disposal, it's a little bit easier. But that is a path we want to go more toward, because the way that Pelosa represents your data is kind of ripe for that kind of thing.
Yeah. Yeah, that's fascinating. Could you build? Yeah, I'm thinking like you could build embedding layers, embedded like latent vectors out of the bitmaps themselves to transform into a new domain, and then invert, like run the process backwards to get a new bitmap out. What would you? I don't know if you care about that in the binary case. I don't know. That sounds awesome. And we're running out of time, and I want to cover one more huge topic here, which is what's Pelosa written in?
Pelosa is written in Go.
Huh. What's that about?
So Go is a little bit of a newer language. I think it was first open sourced in 2009 or something. And it was designed at Google by a bunch of really old kind of Unix diehards, from the early days. And they basically, the origin story is that they were writing a lot of C++ at Google, and they were getting really, really frustrated with how long the builds were taking. Because Google has all this awesome build infrastructure, and you can shard your build out across a billion computers or whatever it is, but they were still taking like 45 minutes. And that's because there's sort of fundamental limitations in the way that dependencies are specified, and the way that C++ pulls in files when it's compiling things. And so they were like, they had all this free time when their code was compiling, and they started thinking about like what the ideal language would look like for them. And that turned out to be this like very pragmatic, very pared down, minimal programming language with really good support for concurrency. And so what they say is that Go is designed for programming in the large, or really for software engineering, where you have, tens to hundreds to thousands of programmers, and your code is running on thousands to hundreds of thousands to millions of machines. And it turns out that in that case, like, you don't want a language with a gazillion different features where, everybody can do something a little bit differently. You want a language with the absolute minimum set of features so that a new programmer can come on, look at the code, and get familiar with it really fast, and not have a bunch of gotchas and foot guns and all kinds of weird things. And you also want it to be efficient. And of course, you want compile times to be really, really low, because that was the whole reason that they started thinking about it in the first place. And so Go is a language kind of designed with all that in mind, and they've done a pretty good job. There's definitely still some problems with the language. It's still got kind of its rough spots, as any language does, but it is a very readable, minimal language that allows you to write very efficient code.
So compared to something like C++, it's sort of not got those higher level features and stuff. What's the like library support or dependency support? Is there a community for that stuff?
Yeah, the Go community has gotten pretty large. I think they have like 40,000 people on their Slack, like the Golang Slack, and a similar number of stars on the GitHub repo. And by some counts, there's a million odd Go developers in the world. So it's definitely not small anymore. The standard library is fantastic. It's definitely not where Python is. I mean, or Java or something like that. There's definitely specialty things that haven't been done or haven't been done and optimized to the degree that they are in other languages. But for a lot of tasks, especially ops tools and just kind of like server-side data processing code, it's a really fantastic language.
Is it fast like C?
Yeah, it's I think if your code is like highly CPU bound, the rule of thumb is that it's going to be a factor of 2 to a factor of 3 slower than C or C++. And maybe that sounds bad, but it's really not. It's pretty close. And if your code's not CPU bound, then it's probably going to be right there. It is garbage collected, so you do have that to contend with. But I mean that usually turns out to be a pretty good idea, as we see from the bug reports that keep pouring in of horrible vulnerabilities.
Are you allocating memory and all of those absolutely nonsensical things too?
Sorry?
Are you allocating memory and dealing with memory structures while you code too?
No, it's garbage collected, so you don't have to manually allocate and free memory. Oh. Although it turns out that sometimes, very occasionally, you do want to do that because the garbage collector can get in the way. But Go's garbage collector is pretty well tuned to not interrupt your program much. I don't know if you all have done much Java, but Java, at least a few years ago, was pretty famous for the garbage collector pausing your entire program for seconds at a time, while it kind of did its thing.
Oh, that's cool.
Well,
so would you say, is it one of those languages that's kind of worth learning, so to speak, because it's got such interesting idioms, or can teach you something about computer science? Or
it's definitely worth learning, mostly because the cost of learning it is so low. I mean, there's just not much to it.
Right.
But the idioms that it does have, I mean, you will not think about concurrency the same way after writing some Go, or writing enough Go to kind of get into it, because you can easily write a program that you spin up and it just pegs every core on your machine at 100%. And that's like such a beautiful thing when you're trying to eke out every last bit of performance.
That's pretty cool.
And I mean, just so at Humble, we had this big Python Django code base, and I started rewriting bits of it in Go while we were there. And I mean, the performance improvements are just drastic. I mean, it's like 50x is not uncommon. It's because of both the concurrency support, and also just because it's a compiled language with a relatively good compiler.
Right.
Yeah, I mean, you're going to do better in C or C++ or Rust. I've heard a lot of good things about Rust. But for kind of all around ergonomics, goes pretty nice.
Awesome.
Yeah, very cool.
What are you reading at the moment, Jaffee?
So I've been cranking through a lot of David Foster Wallace, and the one I'm reading right now is not one of his more famous ones. I think it's called like The Broom of the System, and it's really weird. A lot of his stuff is kind of weird, but he's a really good author. I mean, the stuff he comes up with is really interesting, and sometimes it's incredibly informative too. I just read this one called The Pale King, which is all about like the IRS and the inner workings of the IRS, as told from like the point of view of like various employees and people associated with it.
That's awesome.
Yes, it's really wacky stuff. But most of his stuff is really nice to read, just because he's such a good author. He has a way with prose.
Huh, that's cool. I need to read some of his stuff. I recently read what is it in that book? Bad Blood. It's the sort of manifesto of the Theranos story, written by the Wall Street Journal author who broke the story or whatever. But it's sort of written the same way. It's told from inside out. There's a huge amount of internal references from the company. It's kind of a fascinating book. How about you, Matt Hall?
Yeah, I'm reading. We teach a course in Python, Matt.
I don't want to sound like I'm knocking Python too much, because it's obviously like an amazing achievement, and it's a good language, and the data science support in Python is incredible. So I don't want to sound like I'm knocking it too much. But if you're doing like back end stuff or high performance stuff that's not data science related, there's other things out there.
Yeah. It's always interesting to hear about other languages. But yeah, we're mostly teaching beginners, and as a sort of graduation gift at the end of the course, I give out a book of some kind to all the participants, and I've used a few different books in the courses we've done. But last time, I can't remember why, but I used a new one. I chose Algorithms to Live By two guys, Brian Christian and Tom Griffiths. One of them is a journalist who seems to have taken care of the writing, and the other one I think is a psychologist or some kind of at least semi-scientist, and clearly knows quite a bit about computational methods and stuff. So what they've done is essentially it's a popular treatment of a bunch of algorithms, from kind of stuff like sorting to weighting, early finishing. I'm only about halfway through the book, so I don't quite know what else they're going to cover. But lots of them are familiar to anyone who's done a lot of scientific computing. But they've done quite a good job of really cataloging them and unpacking some of them and telling a bit about the history, like where this algorithm came from, what it was developed for originally. But then trying to sort of map it onto everyday life and say, you can sort out your to-do list like this, with sort of these theories of what's the most efficient order to do jobs when you know roughly how long they're going to take, stuff like that. So it's which I thought at the beginning, I thought, oh, this is a bit kind of cute. I'm not sure, I might skip these bits, but actually, it's kind of interesting.
I use binary search all the time.
Yeah, there you go. Binary search is what, but it is one of those things that is totally non-intuitive, I think, to people who don't know anything about computer science. Yeah. But it's like a magic thing. Anyway, so if nothing else, these little analogies and mappings onto everyday life give you another way of explaining stuff in the classroom. It's like another kind of heuristic or analogy that you can use. So I quite enjoyed those. But so yeah, I think to most computer scientists, they're not going to learn a lot about the algorithms, but it's been quite an interesting read. I'll probably finish the book, so if that's anything to go by. What are you reading, Graham?
I'm reading a book called Never Home Alone by Rob Dunn. The book was recommended to me by our mutual friend, Sebastian Good. It is a study, or it's a cross-section of a bunch of studies this author did on the bugs that live inside of our homes. Oh. So from bacteria scale to insect scale. Okay. It's disturbing and fascinating, and I totally recommend it.
Has it got pictures in it?
No, not really. I mean, there are some pictures, but
normally I have to have pictures in books, but that sounds like a book where you don't necessarily want any.
Yep. Okay, well, Matt Jaffee, thanks for joining us, and we look forward to potentially having you back on the show. That would be cool to dive into some details and maybe talk about a use case.
Right, this has been super fun. I can't believe it's been an hour already.
Yeah, and I want to find out what molecular is. So we got to have you back sometime.
So let's leave it for a future one.
That's it. All right, everybody. See you next week. Undersampled Radio.
All right. Cheers. Oh, I've got to do the
thing. We're professionals.
I'm doing it. You see, the thing is, what I'm trying to do now is get my mouse from one computer to another computer.
Nice.
That's advanced stuff.